All right, page 8, 5-4, central limit theorem. All right, ready, set, I'm going. So it says, central limit theorem tells us that if the sample is large enough, the sampling distribution will be normal, even if the population distribution is not. The charts below show what happens when the sampling distributions shows what happens to a sampling distribution as the sample size larges. Okay, so if you had an original population, and let's say you had graphed your data and it looked like this, so exponential decay, that if you had just 2 people that you surveyed, it starts looking like a little bit like normal, okay? Though this is skewed right a little bit, okay? As I move it to 10 people that in our sample, it starts approaching a little bit better. And if we go to n equals 30, you really create a much nicer normal distribution. So mathematically, and I don't know why, but mathematically, a sample of 30 of an entire population, if it's randomly selected, should give you a normal distribution. 30 is like the golden number. And I don't know what's perfect about 30. I just remember it's always been told to me it's 30. I don't know what the proof behind it is. I don't really care what the proof is. Kind of like the fact that just if you have 30 or more, you're good. Okay? As you can see, the original distribution is sharply skewed to the right. However, the sampling from the parent population still results in a normally distributed sampling distribution when the sample reaches a certain level. Through lots of experimentation and studies, statisticians have concluded a sample size of at least 30. Okay, the sampling distribution of the same mean will form a normal distribution. So I guess years and years and years of doing way too much statistics, they found that 30 is this comfortable zone. Okay, so please take note. When you're applying a normal distribution techniques to a distribution that is not normally distributed, it's a huge red flag. So if you knew this was the entire population, okay, and then you decided, okay, we're going to randomly sample 30 people and we're going to get something that looks like this. This is not, a good thing to do. You can't be like, oh, look, magic happened, therefore it's now normal. Okay, so it's a huge red flag, but it's something to look for. So if you can know the entire population, the mean and standard deviation, and then the sample mean and the sample standard deviation, just be very cautious about how things will happen. The reason why this is going to result in looking like this is, if you recall back, we changed the standard deviation of a sample when we used this equation. So this changes the standard deviation significantly. Okay? And that's something that's big to note. So just think about the math behind it. If I take the square root of something, if I take a standard deviation that's from a population, and I say, or the entire population, and I take a certain group of people, that standard deviation is going to get smaller and smaller and smaller, and that's your margin of error that's going to start taking place. Another diagram demonstrates the theorem. In fact, the central limit theorem is the foundation for all of inferential statistics. So if you look at the graphs below, you have normal distribution, uniform, exponential, and parabolic. And then the sampling distribution of 2 would keep the normal distribution somewhat normal, but then you create a triangle. Then after that, you kind of create something that's definitely skew right. And then you get to something that actually looks like you're flipping somebody off. Okay, if you're on page 9, you'll see what I mean. And then if the sample becomes 5, it changes a little bit. Again, the normal distribution stays relatively the same. The uniform starts turning to looking like a little bit more of a normal distribution. You still have skew right with 5, and then you have all these waves when it's a sample of 5. But if you go to 30, then all of the sampling distributions, regardless of it is normal, uniform, exponential, or parabolic, all turn into a normal distribution graph. And some will look a little different. So it doesn't matter that the population distribution is, if the sample size is 30 or larger, an extremely close approximation of normal distribution is formed. But again, realize because you're manipulating, you're not changing the data, you're just doing different math principles to it. You know, if we were, for any of those, if I had the, oops, sorry about that. If I had n equals 2, that's going to be standard deviation over root 2. If I did n equals 5, and if I did n equals 30, this would be the smallest number. Okay, so your new standard deviation goes from being a little bit spread out to getting closer, getting closer, getting closer, getting closer. It gets closer and closer and closer to what your average is. And that's kind of a, you know, kind of the key to it that goes there. So my warning, and I've said this before, and I know, and I've tried having quizzes in place that have been, you know, much easier, smaller, but more easier to try and inflate your grade, because unfortunately 5.5 and it's 5.6 and 5.7, they're going to be a lot of the and even when you get to the test, so make sure however you're doing your notes, you're highlighting, you know what you're going to put on your note card. Will definitely be helpful for you, especially the vocabulary of each of the events, okay? So this is what I have for you. And I'll give you time now to work on it.
So can you go over the first?
Yeah, let's take a look. So let's go to page 73. Am I on the right page?
Yeah.
Okay, why don't I go and I'll do the odds.
Okay.
Sound good? So page 73, let's look at problem number 1. Okay, it says for problem number 1 on page 73, it says the migration distances of birds are known to be normally distributed with a mean of 3,600 miles and a standard deviation of 350 miles. We wish to know the probability of a random sample of 20 tagged birds will show an average migration distance over 4,000 miles. Okay? So, being that the population, mean, and standard deviation show normal, or at least they tell it is normal. Therefore, the sampling will also show normal. Okay. Now, I know this information. You know, there's different things going on with the climate. You know, migration of birds is actually getting less and less and less. Why is that? Because temperatures are not what they used to be. Okay. Remember when you were a kid and we'd have 3 feet of snow still sitting outside? I don't know. I've started recognizing trees are starting to get buds on it and looking like they might start getting leaves. Doesn't mean we're not going to get slammed with snow, but that, of course, messes with the bird population. But I know a lot of stuff with birds, they were able to see based on just looking at something as simple as birds going, there's something going on in the environment that these birds that we are tracking are not traveling the distances anymore. But that's more of the science aspect to it. Okay, number 3 says we wish to know whether a random sample of 20 cars on I-70 at rush hour will show an average speed greater than 50 miles per hour. characteristics of the population of speeds of cars on I-70 during rush hour are unknown. Okay, so they want to sample 20 cars and see that. So this is our sample of 20 cars, and that we have 50 miles per hour as an average speed. Okay, well, the sample size, one, this is not 30. Agreed? So this is not 30. So be careful. Okay, it's not going to give you necessarily a normal distribution. It could, but that would be coincidental. So the 20 is, you're like, well, it's close enough. Well, close enough. Don't fall into that category. Okay, so the sample size isn't large enough. It's not above 30 to ensure normal distribution. So this, not 30, so won't ensure normal distribution. Okay, I guess what it comes down to is how do you actually take a random sample of 30 cars? You'd have to guarantee people are going to be on I-70 during rush hour. And then how do you honestly randomly sample it? I guess what you could do is you could say, take a random number generator, which we saw was flawed on the graphing calculators, but we could start assigning numbers to cars, as they go by. And you say, okay, that's the third one. That was part of our number. Now we need to find the 17th one. There's the 17th one. 26 was another one. And I'm just making up numbers arbitrarily. But I'm just saying that's how you could go through that. For number 5 on page 73, let's see. It talks about anxiety can often be measured by a trained psychologist and can be scaled between 1 and 100. Anxiety as a population parameter is skewed right. The mean anxiety level is 30 with a standard deviation of 20. So they're saying that your distribution of your population is that's supposed to be skewed right. So maybe I could draw that a little better. Okay. So they're saying the mean is 30 and the standard deviation is 20. Okay, so what is the for number 5, what is the probability that a random sample size of 100 will show the anxiety between 28 and 32? So we're trying to go between 28 and 32. We're doing a sample size of 100. Okay, so we need to figure out what our, let me get the terminology right, the equation correctly. We need to say that this is equal to the standard deviation over square root n. So they're saying that you had a sample standard deviation so we're saying that we had a sample size of 100. Anxiety population skewed right. The mean anxiety level is 30. Standard deviation 20. Okay, so they're saying this. 30. Nope, I take it back. This should have been 20. Standard deviation was 20. And square root of 100. So you're doing 20 over 10. So you're getting a standard deviation of 2. Okay, so this is our new sample standard deviation. Okay, so friends, what do we do? The 20 was our original.
Oh no, that's standard deviation.
Standard deviation, yeah. Of our entire population. Now the 20 was the standard deviation of the population. But then they say, hey, we're going to create based out of 100 people, so square root of 100 is 10. 20 over 10 is 2. So now we have a mean of this. We're going to keep our mean, but now we're going to do this as standard deviation, and we want to do this. So how do we do it? Yeah, let's bust out some calculator stuff. So let's see what happens here. Let's let it warm up. Trying. Just thinking. Are we going to go? Somebody have a calculator with them. Oh, here we go. I got it. All right, so normal CDF, it's set up for us. Actually, let's quit out of this. Clear. Normal CDF. So our lower limit is what? 28, then 32. And what was our standard deviation? Our mean was 30. And our new standard deviation was 2. So you're looking at 68.3%. That what is probability? What is probability of random sample size of 60 or 100 will show a mean anxiety between 28 and 32. So we're looking at 68.3% of the population would fall in between those two. Hi, John. Okay.
So, Stuart, when it says note any red flags that might undermine your solution, what does that mean?
Let's see.
Just at the top, above 4, 5, and 6, it just says note any red flags.
Note any red flags. That means that, so looking at this one, it doesn't appear we should have any red flags that are showing out. It's not like they took a sample of just people in Denver or anything like that. It appears to be, I guess you could say a red flag is where did we actually come up with those 30 people? How did we randomly select it? Those could be red flags, but technically I don't think, I mean, if you were to put everything about every study on every problem would be, a half to 3/4 of a page in length telling you everything about it.
That's fine.
But I don't think, being that they said that, you're looking at psychologists, so you, the reader, are thinking, are you talking about psychologists nationwide or worldwide? You don't know what tests are given. I mean, there could be flags in that kind of situation, or we can just trust what the writer is trying to convey to the reader. Okay?
If the problem had said, like, measuring people just in Denver, that would be a red flag?
Yeah. Or in any particular area.
Okay.
And then, you could ask, where is the population, like we said. Let's see, anything else to that we could say? We also might be able to say, how many people are involved in this study. We don't necessarily see that, but they're just giving us what they found. So hopefully when you see kind of stuff like that, you could question how many people are you talking about. Hopefully it's above 30. If it's not, then, shame on them.
Okay.
All right, number 7. Number 7 says, find the probability a sample of size 25 will show a mean anxiety between 28 and 32. Okay. So we're changing sample size to 25. What's our red flag right now?
It's less than 30.
Yeah, so we have a red flag. So this is less than 30. So red flag. Doesn't mean we can't try and do it. It's just we have to recognize mathematically we probably wouldn't accept it. So the sample size 25 will show anxiety levels between 28 and 30, 28 and 32. So this is going to be the normal CDF. where we'll do 28, 32. Find the probability sample size. 25. Okay, so we know that our new standard deviation is going to be this. I guess we're continuing from the previous page. So standard deviation, they told us originally was 20, and we're going to go over root 25. So 20 over 5, so you're getting a new standard deviation of 4. So if we went with that, I can put the 25, nope, I can't. Where do we put the 25? And the 25 has already been accounted in this new thing, so we still have 30 here because we were saying originally that was the original mean, and then the standard deviation is 4. And if we did that, our normal population is going to yield us 38.3%. Okay, so if you look back at a problem, this one was a little bit nicer. I forgot what this answer was I'd given it. But this one, this is a more exact than 7. And then problem number 7. The reason it is because we're talking about 100 is our sample. Whereas this one, this gets goofy, or this is what their new sample is. So that's the information you could list about that. Number 9 says the length of films released by Hollywood are known to be normally distributed with a mean of 115 standard deviation of 15 minutes. So this is for problem number 9. So they're telling us that we have a mean of 115, standard deviation of 15. Find the probability of a random sample of 9 films. Is there a red flag here? Yeah, that's less than 30. So it's kind of bad, but we can go ahead and work with it. And this is going to be normal CDF of 120. Show a greater time than 120. And then this needs to be something larger. So like, let's make 1,000. And then we know that we had 115 minutes. And our new standard deviation that we're going to use off of this is the 15 divided by square root of 9, which is 15 over 3, which is 5. So our standard deviation is going to be 5. And this is going to give us 15.86% of the area under the curve. But again, we have a red flag on this one, so we shouldn't trust it. And then problem number 11 says, assume the average electric bill is skewed to the right. So remember, skewed to the right is going to look like this, with a mean of 145 and a standard deviation of 50. If this is skewed to the right, that just means we have a greater amount of people that are using a lot more energy. They're keeping their house at 68 during the summer versus, whatever Excel asks us to do. Let's see, 50. What electric bills are at 1 standard deviation above the mean and 1 standard error below the mean? So I'm going to draw a normal distribution. So this would be our standard deviation each way. So here's our mean, standard deviation, standard deviation. So we want to know this, and we want to know this area. So we have to do normal CDF twice. We have to do that twice. And so we'd have I'm going to call this A, call this area B. So this will be for area BA. We could have 0, 1 standard deviation below that is min to standard deviation below. Let's see. That's to 95. And then 145 to 50. And that should give 132.5. And then if I did normal CDF for B, that's going to tell us that we're going one standard deviation above, so whatever that would be. So 145 plus that, we're going 195 to like 1,000. 145 to 50. And that should come out to 157.50. Okay, so you're looking for the other tails. Okay, so for the homework, I would like you to complete page 75, 76. Wait, am I on the right page? No, I'm not on the right page. Sorry. Page 73, 74. And get the evens done. Cool, and you can work on that rest of the period. Ask me if you have any questions. Let me just pause this.